Hello everyone, I'm Kartik Krishna. In this video, I'll be talking about our work on navigating unsteady flow fields from finite time Lyapunov exponent to energy optimal trajectories. So a lot of the motivation behind this work comes from the fact that we have autonomous marine vehicles and we want to deploy them in the ocean to improve our capacity for transportation, surveying ecosystems, and weather and climate monitoring. And a key aspect in being able to do this is the problem of navigation. So what do I mean by this? So imagine that we put one of these autonomous vehicles in our flow field. So you can see the white dot, and you can imagine one of those is our autonomous vehicle, and it's moving around. And what we want to do is we want to propel ourselves to another point in the flow field. And the real question we want to ask is what are some good control actions so that we'll be able to do this? So how do we fire our thrusters or propellers or shift our buoyancy or whatever we have on our system to do this? So a key challenge in this in general is that a lot of the autonomous vehicles that we have limited computation capabilities on board, limited actuation, and limited ability to communicate. So they have to come up to the surface to be able to exchange any information. And the ocean is this rough, chaotic terrain or environment with rogue waves and really strong currents. And what I really want to emphasize here is that you are often not able to move override the currents. So the ocean currents often will drag you along wherever it takes you. So how this translates in the design of trajectories is that on the left, you have this trajectory just shooting straight across the ocean flow field. And you won't be able to do this usually. Usually what we want to be able to do when constructing good trajectories is we want to use the flow field and the ocean dynamics to move around. And you want to use the minimum required force to hop across different level sets of your flow field to get to where you want to go. And so the aim of this work in general is to understand the relationship between the dynamics of the flow field and the trajectories that you form in the ocean. So to get more specific, this is the vector field that we'll be using in our work. It's the double gyre flow field, and it's a periodic flow field which moves to the left and right, as you can see in the video. And one thing you should take note is that even though the flow field is periodic, the trajectories individually in them are chaotic. So they show sensitive distance to initial conditions. So two close by vehicles dropped in the flow field can end up in completely different places. And the model we're going to use in all the simulations I'm going to show in this video is the one I've kept below. It's called the kinematic model, and what we're saying is that the velocity of your vehicle is equal to the sum of the double gyre flow field and the propulsion given by the vehicle. And the parameters we're using for the double gyre comes from the Shadden Physica D paper from 2005. Okay, also, the next ingredient in this is model predictive control. So what we want to in this paper, the way we're designing our trajectories is that we have our cost function. We're setting up a cost function, and our agent at every instant is forecasting ahead a model of where it'll be, and it's finding the best control actions it can take over that small finite prediction horizon that it takes. And this optimization is constrained subject to the vehicle dynamics and the limitations in actuation. And we re-optimize at every single step so that this gives us robustness to uncertainty or any unknown effects that we haven't modeled into our system. Okay, so right off the bat, we have many parameters that we can play with. So the first one is the time horizon. So how far ahead in time you can forecast, or how frequently you should be measuring your vehicle position, and how frequently you should be running this optimization. And the third one is the ratio of your energy penalty to your state penalty, and I'll explain what this means along. It's an intuitive way of saying what's my tolerance for error in my simulation, and how much battery life am I willing to pay. So I'm going to keep the time horizon and the sampling rate, time rate fixed, and I'm going to sweep through different R by Q ratios on this. And what we want to take note of here is how the color of the trajectory changes, which means how the energy is being spent. Towards the right, a general trend you can see is that things are getting more and more purple, and the tightness around the goal. So if you see the leftmost figure, you have this really tight orbit around the goal, but and it's loosening up as I increase the R by Q ratio. And another aspect to notice is that all of these closed loops around our goal is our hovering states, which are periodic orbits. So they're moving in these loops, continuous loops, with no loss of being dragged around chaotically like the ocean would normally would. Upon increasing the R by Q ratio further, we do hit this point where the trajectory orbit is growing larger and larger in size, and suddenly it switches completely to a different qualitative trajectory altogether. And this can be thought of as like a bifurcation of some sort in the space of all trajectories. In fact, if you sweep through more and more R by Q ratios, what you find is that there's this entire zoo of trajectories that you can build with which use energy really differently. So going towards R by Q equals 78, you have these massive loops around your goal state. A physical way of really understanding this is thinking about each periodic orbit as a periodic orbit of battery power. So if you have a lot of battery on your autonomous vehicle, you can go on this very tight state around your goal. But at low battery capacities, you can hop on into a larger hovering state around your goal orbit. So one question you can ask is, how does the energy vary along these trajectories? And we want to look for deeper connections and understand more about how these trajectories are associating with the background flow field. So a really powerful tool from dynamical systems which could potentially allow us to do this is the idea of Lagrangian coherent structures. So to those who are unacquainted, Lagrangian coherent structures are these curves in your vector field that you can calculate by integrating forward a grid of particles forward and backward. So there's two kinds of LCS. There's attracting LCS and there's repelling LCS. So the red curves are attracting and the blue curves are repelling. And what they're attracting is if you drop a dye or any kind of tracer particles into the fluid, the red curves tend to attract the tracer particles, whereas blue curves likewise make the tracer particles repel away from them. Key point I want to emphasize is that just like model predictive control, the computation of Lagrangian coherent structures using the finite time Lyapunov exponent has this aspect of finite time forecasting in it. So you are integrating forward in time for a finite amount of time, just like you're forecasting in model predictive control for a finite amount of time forward. So connections have been made in the past between the generation of optimal trajectories and Lagrangian coherent structures. So in 2005, for example, it was found that optimal trajectories tend to overlap a lot with Lagrangian coherent structures. And in 2008, people tried using a line following algorithm to follow the Lagrangian coherent structures to bring this energy optimal trajectories forward. So in this slide, we're going to bring back MPC and we're going to run it keeping our parameters fixed. And we're going to start visualizing the Lagrangian coherent structures in the background. So a couple things that we can start noticing is that the forecast tends to overlap with the curve shapes of the Lagrangian coherent structures. The drifter takes a lot of time moving with the LCS, which you'll see in a bit later. And also another thing I want people to notice is how we start hopping from the red LCS to the blue LCS. So I'll try playing this for a while. So at this point, we start moving on the red LCS, and then now we start hopping towards the blue LCS. Another aspect that we observed across our simulations is that whenever the drifter is crossing the blue LCS, it starts trying to spend more energy to get across it. And this might be particular for the hyperbolic time type of LCS in the middle, as opposed to the shear driven LCS in the edges of the gyre. So on this final slide, on the left, I have a picture of the world map of Lagrangian coherent structures in the ocean. And on the right, I have a picture of all the Argo floats that have mobile robots that have been deployed in the ocean at the current moment. There's about 4,000 of them. And over the course of the last few slides, we've seen that there seem to exist a coupling between the dynamics of the flow fields, coherent structures, and trajectory generation. And there's a lot of opportunity to explore and exploit these phenomena. There's also recent work which really aids us in the practical, brings us closer to the practical implementation of these methods, where you can use multiple vehicles to estimate background LCS. So this would be able to help us with multi-agent trajectory planning and things like that. So finally, I'd like to say thank you for listening, and there'll be a paper available on archive soon. And I'd like to acknowledge our sponsors.